Okay, welcome to double integrals and volume. Now this, we've seen how to set up the regions of integration. We'll be doing that again, of course. But to find a volume of a surface given to us by a function of x and y is we evaluate the double integral of that function across the region of integration dA, which dA is either dy or dx or dx dy. Sometimes the order doesn't matter, as we've seen, and sometimes it does to be able to integrate it or make it easier. So we learned last time that actually if you don't have a function there and you're just integrating dA, you're finding the area of the region. In this case, the region would be that triangle with the curve, not really a triangle, I shouldn't say that little arc segment right there on the bottom. And since z is essentially f of xy, we've already learned that from back when, that would represent the height of the function. So basically it's a fancy mathematical way of indicating area times height to give us our volume. Now, of course, one thing to keep in mind when we're doing volumes is, just like an area would have to be, your answer has got to be positive. One thing I didn't mention, when you're evaluating double integrals in general, if it's not set up to calculate specifically volume or area, the result of a double integral, just like a single integral could be negative, positive, or zero. But now, with being volumes, or they have to be positive numbers. All right, now one thing to keep in mind that this gets people confused sometimes is that you're never going to be really sketching this function, this three-dimensional function. So don't worry about, like, oh goodness, am I going to have to draw these things in 3D? Now some of these, like this paraboloid's pretty easy to make a rough sketch if we need to, and something called a tetrahedron, I'll show you what that is in a minute. That's easy to draw, but that's not, z equals x squared times y squared is not exactly a trivial type of sketch. So when we're sketching regions, we're only sketching the area if we need to sketch to take a look at it for whatever reason. This one, I just did it to practice reversing again, and this one's already set up to work out. It's not volume, but once again, you never have to worry about graphing that x squared y squared part ever. So I did over here on the right, I let Maple do it and got 256 over 27. Now I said reverse the order if we want. Of course, that could be its own question, but let's just do that for practice. So I graph them. If x equals 1/2 y, that's y equals 2x. And if x equals the square root of y, that's y equals x squared. So from dx means left to right. Now, not lower to upper, left to right. The line is on the left, y over 2, and the curve is on the right, square root of y. But you see, now I've changed them to be y in terms of x if I want to do this in dy dx order. So now we would look at this lower to upper with dy on the inside. That means your variables can either be it can only be x, or it can be, the limits can be numerical also. But lower to upper, both of these are variable. They change. They both change. Lower to upper, x squared on bottom, 2x on top. And then on the x-axis, left to right would be 0 to 2. Outside must be numerical. And we already know from what I put in Maple up here, I know that 256 over 27 is the right answer. So this setup I have here certainly better yield 256 over 27. And let's see what we have here. All right, so pretty easy to work out the mechanics here. Dy, so you do y first, so x squared just sits there. 1/3 y cubed, put in 2x, put in x squared, and I put the 1/3 on the outside. You'd have the x squared still sitting there, and then this 2x cubed makes 8x cubed, and then x squared cubed makes x to the 6th. Of course, you'd want to distribute the x squared before you go to the next step, and to get them into individual terms, and now you have just two individual terms to integrate, two power rules. And then you got the 1/3 there, you put in 0 over 2, blah, 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 you get 256 over 27, which is the same answer. So that's probably means I reversed those correctly. Oh, this is, had this been set up as a volume problem, it wasn't asking for that. We actually did find the volume. Yeah, I didn't, probably should have rotated these around to get different views of this. But remember, you're not sketching that z equals x squared, y squared. On the bottom down there, see the red and the blue lines right there. Keep in mind the way the x and y axis are written in 3 dimensions. It's kind of tilted. But that right there, the blue and the red, is what I have drawn right there. Just wrote, this is the normal way you're used to looking at the x and y axis, versus rotated around it looks like that. So that's the same region on the base. So actually that calculation, what it's finding here's what you imagine is, if you take that area region and around the perimeters, the entire chunk of it, and you lifted it up to this surface, and the volume formed inside that area region as it's lifted up and meshed in with that surface, that's what the volume is, like cutting out a wedge, lifting up there, and that's what that calculation measures. The portion of volume under this curve, but inside that area there, all the way down to the x-axis. So, yeah, I wish I could get a good picture of what that means. This picture up here is a little bit better, I think, if you see that one. That's what you can tell. You see that little region of integration on the bottom, and it's lifted up to be along this curve. So that would represent the volume of that little wedge piece taken out of there using that base with this height. Harder to see from that maple one. Maybe I could have rotated it around a little bit, but that's okay. And then, so if you ever use maple for anything, I just use some variable names of students that were in my classes when I did it. So obviously you wouldn't have to use silly names. You can use whatever letters you want to use for variable names. Call them, like, I don't know, R1, R2, R3, whatever. Now this didn't mention this in the last section, but we didn't need it now. But now is a good time to say it. I have said, of course, the outer limits of integration are always numerical. But the only way that you're ever going to have, if you're setting up a problem, obviously if it could be given to you that way, but this one we're setting it up. The only time that you ever have a problem where the inside limits are also both numerical, not one number, one variable, numerical inside, numerical outside, is if your region of integration is a rectangle or square. Of course, a square is a subset of rectangles. That's the only time it'd be numerical, because you look at this, nothing changes left to right. They're both fixed amounts, the same number. Lower to upper, it's fixed. It doesn't vary at all. So that's the only time we have when they're all numericals, when it's a rectangle. All right, so I just kind of plotted those points and then drew that little graph there with those vertices. And this isn't a hard problem. Just be careful that you remember from basic Cal 1 that the antiderivative of sine is negative cosine. So put in pi over 2, put in 0. That ends up with, you could reverse it. I could get rid of that negative, and I could use that property and reverse it. But you'll end up, that's 0 minus 1, so negative 1. Negative 1 is positive 1. So that produces positive 1. That's why you don't see, oh, there it is right there, 1 minus 0 by reversing it. And that goes away, so you integrate sine of x, and you get negative cosine of x. Pi to negative pi, then ends up being 0. Okay, so this integral ended up being 0. It wasn't designed to calculate volume. Now, I didn't graph this, but what that usually would represent is, if you think of 2 dimensions back in Cal 1, do a real quick sketch here. 2 dimensions. Can't really draw 3D that well, but I'll just tell you, in 3D, that just means the same amount of your graph that's above the XY plane is also below the XY plane. So if you integrate it from beginning to end, they essentially cancel each other out. Now keep in mind, this graph's not going to be perfect here, but if you did, so assuming this is symmetrical, that those, you're trying to find that total area. Well, if you went straight from A to B and both those regions of integration are the same, that definite integral would work out to be 0. because you have the same amount below as above. So the proper way to have done that with single variable integration would be to go from A to 0 and then from 0 to B and add those two together. So this problem, so this kind of goes back to what I was saying a few minutes ago. So sometimes but that's okay that worked out to be 0. We weren't implying that was supposed to be a problem. It was just strictly a calculation issue. So that was all right that it came out to be 0. Not supposed to be a volume. So here's one where we have to just work out the double integral. Also, this doesn't imply it's a volume. So instead of giving us the limits of integration, we have to get them ourselves. And based on how the region is defined. So that's where a graph's going to come into play here. Once again, we're only sketching the two-dimensional region of integration. We are not sketching that function, y over x plus 1 plus x squared, thank goodness. But so y equals 0, y equals square root of x stops at 4. So there's a boundary that closes it off right there. And in this case, I would just go, well, I guess let's see what order would be better here. I don't think it matters. I set it up in both orders just to show you. Let's see which way I chose to work it out. It looks like I chose to work it out dy dx, but I did set up both of them. That's why I have the y equals square root of x and x equals y squared to be able to reverse it. So dy dx, you would go from 0 to the curve. So it would be 0 to the square root of x, because if dy is on the inside, remember, these must be either numbers or x's. 0 to root x, and then x going horizontally would be 0 to 4. So that's one way. The other way, you would read this as left to right. So the curve is on the left, the line is on the right. So x is going from y squared, and x is going to a fixed value of 4 right here. Lower to upper must be numerical. So it would go from 0 to 2. That's hitting 2 right there. 0 to 2. Now you see I came over and decided I'd put this one in Maple. Came up with 1/4 log of 17. And I just chose to work it out the other way. And let's see what happens. So the antiderivative of y dy, because we don't have to worry about the x squared part yet, would be 1/2 y squared. And then you put in square root of x, put in the zeros, so square root of x squared is x. I toss the 1/2 out to the outside. All right, so that yields us just a substitution integral, just basic U substitution. And 1 plus x squared, 2x, 1/2 du. U of 4 will be 17, U of 0 is 1. So you're basically you're integrating either du over u with a 1/2 on the outside. So there's two 1/2s here, by the way. There's a 1/2 that was there from the y squared, and there's a 1/2 that comes from this du right there. It's well, it doesn't matter which one they are, but there are two 1/2s. So that's why, like 1/4. U to the negative 1 du is the same thing as du over u, and remember that's natural log. So always remember, if u is to any power other than negative 1, you use the power rule. That's the only one where the power rule does not work, and the answer is natural log. So you have 1/4 natural log of u. And just like I told you in the last section that, it doesn't hurt to know that e to the 0 is 1. It doesn't hurt to know here that natural log of 1 is 0. So it's ln of 17 minus ln of 1, but ln of 1 is 0. So you just end up with 1/4 natural log of 17, which is what Maple got doing the other order of integration. And this one actually is a volume. I graphed this one. So there's your region in the red and the yellows in the plane. So just picture that region being lifted up to the edge of that curve, which obviously the curve looks like it's running real close to the XY plane right there. I could have used a couple more angles on this. But there, it's underneath it right here, so you can see it goes up there. So whatever 1/4 natural log of 17, natural log of 17 is probably around 2 point something. Well, actually, maybe it's closer to 3. Well, there doesn't look like there's going to be much volume under that curve anyway, because you see it so close to the XY plane. But remember, you never were going to be graphing this 3D part anyway. But So it's that region and that area as if it was lifted up to the edge of that curve and created a volume. All right, I'm going to focus on the setup of this problem, and also when we go on to triple integrals later, we'll do the same thing. I've decided in recent semesters that I don't have people work these out anymore, especially when I show you there's actually a very simple geometric formula to calculate this, so it seems pointless. So I'm going to set this up carefully, but I'm going to kind of skip a lot of the algebra steps. It's just very tedious. It's not mathematically complicated, it's very tedious. And I'll show you what I get versus what the geometric formula says it should be. So let's just focus as if we were just setting this up. So to find the volume, so I got to solve this thing, take this equation of this, it's called tetrahedron, but it's a plane, and it's bounded. The first octant means x, y, and z are all trapped at 0, so we're not going outside that first region here. So, but you got to solve for z in terms of x and y, because this is the function you're integrating, is the f of x, y, and then the area base right here, that area, that's what we're going to use as your dA, your dy dx or dx dy. So that's easy enough to solve for z in terms of x and y to get this. So that's what's represented right here in this integral. Now, the limits of integration, you can choose either order. So knowing how to come up with both orders obviously is important. Because obviously I could ask you to set this up in whichever order. Now, when we take this graph and we want to put this down on the xy plane, forget about the third dimension of it, which we've already taken care of right here. Just think of it this way: is just let the z be 0, because anytime you're on the xy plane, that means z is 0, and that just tells you that this line right here will be 2x plus 3y equals 12, which I then redrew in a more user-friendly way to view this, like we're normally used to viewing the x and y axis instead of this way. But it's the same graph, just tilted around to look a little more normal. So let's see what we have here. Now, so we can set this up. I mean, I don't think one order is not going to be easier than the other. They're both about equally tedious, I would say. But like I said, I'm going to kind of fly through that part a little bit. So the way you do this is, if you go dy dx, you take this equation right here, and you know it's variable because it's going from lower 0 to the line. Solve for y in terms of everything else, so it'll be 1/3 times 12 minus 2x, or you can distribute whatever, 0 to that. And then we know on the x-axis it would go from 0 to 6, because that will be the x-intercept. Easy enough to get, right? If you put 0 in for y, 2x equals 12, x equals 6. So that would be the dy dx order. Now to go dx dy, you're still integrating the same function here for the volume, but now you go dx dy. So you go the lower, now you're going left to right now. So I have to get x in terms of y, so the left would be bounded by 0. The y will be the line, but you take 2x plus 3y equals 12. You solve for x in terms of y right here. And then that gives you this setup. And you have 1/2 12 minus 3y, and then 0 to 4 would be your vertical right here on the y-axis. That would be dy, would go from 0 to 4. Now I put it in Maple, I put dy dx and showed it was 12, so just for grins, I did it in dx dy. And like I said, well, I'll just kind of skip through this. You can look through this and then ask me questions. It's just very tedious. Now, to save a little algebra, which it's okay if people didn't catch this step if they were working it out. You wouldn't necessarily be expected to see this, but so anyway, you just take the antiderivative, plug in the limits, and then when you get down to this part right here, and that seems to work. I've never actually derived it. Obviously, it could be derived, but this works this way for these kind of tetrahedron problems every time. Is that when you get this 12 minus 3y, if you actually factor out the 12 minus 3y, the two terms you left with, 6 minus 3/2 y, can be converted to a form of 12 minus 3y every time, or whatever that is. So that ends up being half of this to get this. So therefore, and I wrote it as this, and you get 1/2 of 12 minus 3y squared, and then you can combine it with the other 3 minus y squared. So half of something minus 1/4 of something equals 1/4 of something, and then integrate it from there. But you could obviously work, line it, expand it out, work out each individual term. I would combine the like terms before I integrated, but I mean, you didn't have to catch that little trick, but that trick does work every time for these, although I have quit asking these, integrating these, but I may bring it back at some point in time, so I want to leave them in the notes. So I chose to do U substitution. You might want to square the binomial, which of course is not 144 plus 9y squared. You'd be surprised how many times, even in Cal 3, people mess that up. If you want to expand that out, it would actually be 144 minus 72y plus 9y squared. But anyway, I just went U substitution, worked it out, and I got 12 this way. Well, there, I put it right there in Maple, though. I got 12. Was that the same? Yeah, dx dy, I got 12 there. dy dx, my setup got 12. But let me show you actually what the geometric formula for this is. For a tetrahedron volume, it's 1/3 times area of the base times the height. So if you go back up to the picture, the area of the base would be 1/2 6 times 4. It doesn't matter which one you call the base or the height right there. So the area of that bottom triangle is 12, and the height of that tetrahedron is 3. So down here, 1/3 times 12 times 3 would just equal 12. But like I said, I do like the setup of this problem, how to set it up. So focus carefully on that. But let's probably spare you the gruesomeness of the details on this one. All right, moving along. Let's see what we have here. Now, this one's kind of weird, but because it gives you y equals 4 minus x squared and a z equals 4 minus x squared. Well, don't let that confuse you. The fact that because the z could have been a function of x and y, it just only happened to have x's here. But don't let that bother you. The z equals 4 minus x squared, that's the function you're integrating, because you're always integrating the z equals f of xy. The y equals 4 minus x squared, that's your area region in your base that you've got to work with for x's and y's. So you just kind of graph this, however you want to graph it. Y equals 4 minus x squared. First octant means everything's 0, so pretty much the same thing as the first quadrant, just including z is also bounded by 0. So that's how I would know that that was 0. 0, you go from 0 to 4 minus, well anyway, that's not true, but the 0 is coming from right here, the lower limit, to 4 minus x squared. But the first octant just keeps this trapped, and we don't have to worry about this thing being anything other than this. 0 to 4 minus x squared, and then x would go from 0 to 2. So it's weird with both of them being 4 minus x squared. Maybe I should revise this problem in the future and make that z equals 4 minus y squared or something, just to make it a little bit different so they're not both the same. Not a hard integral to work out, if you had to work it out. Antiderivative dy is just y. It's going to toss a 4 minus x squared in there. So I just kind of foiled that 4 minus x squared out and then just integrated those three terms individually using the basic rules from Cal 1. And I got 256 over 15. And let's see. Did I put this one in Maple? I did not, but that's all right. Pretty sure we did it correctly. Okay, I just kind of did, what did I do here? Oh, I lifted this graph, which I don't know why I bothered to do that, but anyway, that's all right. This green line is the y equals 4 minus x squared, but I went ahead and I made it 3-dimension and lifted it up just so the one that's curving like this, going that way, that's the z equals 4 minus x squared, and this one coming along here is y equals 4 minus x squared. So, and then you see they kind of cross right there. Maybe that's why I did that, to show that it is cutting into that. So the volume is actually then that we're figuring out is this base up here lifted up to the height bounded by those two curves and bounded by that wall right there, and this base and that wall. It's all that volume right in there is 256 over 15. Same thing right over here. So that's just kind of, so I just made it three-dimensional for the y equals 4 minus x squared part. Okay, let's see. Oh, ironically, here is it. I just said z equals 4 minus y squared. That's the next problem, but it wasn't using the 4 minus x squared. Okay, doke. All right, you kind of had to take this base here. So you see, there's your z function. That's what you're going to be integrating right here. The y equals 4 minus x squared. 4 minus y, z equals 4 minus y squared. That's what we're integrating. Now you sort of have to take that base, and maybe you can figure it out without redrawing it. I like to redraw it just so I don't mess it up. So you see I have y equals x and y equals 2, and then I just chose to put it in a more friendly x and y visual here that we're used to. So you see it's bounded between the y-axis and the line x. So that's how I know it's that yellow shading right there. There's the y-axis here, right there, and there it is right here. So it's definitely that upper triangle. So if you go dy dx, you'd go lower to upper. You'd go from x on the bottom to 2 on top, and then x goes from 0 to 2. If you go left to right, dx dy, you'd go from 0 to y, left to right, and then 0 to 2 vertically. All right. Let's see. I chose to use dx dy, and either way is fine. But I'm guessing because I would have chosen that, and it wouldn't have been wrong to choose the other. It has that extra 0 there, so it probably makes it easier. That would be the only reason. Integration-wise, it's not any harder. It just probably means you'll have less terms. All right, so antiderivative gives you an x. Put in 0 to y, so it brings down a y. Then you distribute it, give you 4y minus y cubed dy. Easy antiderivative, 2y squared minus 1/4 y to the 4th, 0 to 2. And that worked out being 4. Kind of weird, you're usually not expecting it to be a whole number answer for something with curves like that, but that's certainly possible. And that's that little wedge of volume right there turns out being exactly 4 cubic units, which we don't have units here. Here's an improper integral. Kind of goes back to Cal 2 a little bit there. I wouldn't worry about the formality of having Cal 2 when we did single integrals, improper integrals. It was important to write out the formal limit notation. Here I sort of took some liberties on this one. So you see this is a graph that's just never going to touch the xy. It's never going to hit the xy plane. It's going to get closer and closer and closer. You see the maple has 4 already as the answer. I guess because it's improper, technically the right answer would be converges to 4 because it's not exact, but that's all right. We'll see what happened here. So I did the u substitution with respect to y the first time, so dx would be 0, dy would be, so it's negative 1/2 dy, and the limit as b goes to infinity of e to the negative b would be 0. So so then you turn out you have the negative 1/2, then makes it negative 2 out here when you divide by negative 1/2. So then you have make that e to the b, put in, that's why I put that, if that's now it becomes b, put infinity in there. It's going to make that e to the negative infinity basically goes to 0. And the e to the 0 though is going to be, because you put in 0 here for y, so the x would still stay there. You put the 0 in for y, you have negative x over 2, but when you put infinity in there for y, it makes no difference what x is, because it's going to go to infinity with that infinity for y. So You've got 0 minus negative x to the e to the negative x over 2. And then, so you put the infinity in for that, integrate that. It's going to give you negative 1/2, which puts a negative 2 out there, which will give you a 4 with the 2 negative 2's. Actually, let's see. I think I skipped a step here, but just because this is positive 2 now, because it's negative 2 times negative positive 2. So when you do the u du thing, you get another negative 2, which will then make it negative 4. Yes, that's positive 2, makes it negative 4. Put this in there. You'll get 4 times 1 minus 0, which is 4. The end.